sometimes it's not easy for us to isolate one of the variables in one of the equations, or it's just going to take multiple steps like it did on the last one. And so we have a second option as to how we can solve a system of equations, and that's called elimination. And so in elimination, what we're going to do is we're going to add or subtract the equations in such a way that one of the two variables is disappear. The same principle applies as in substitution, where we're trying to combine the two equations into one. But now what we're going to do, so long as I've got everything lined up, my x's, my y's, my equal signs, the numbers on the other side, I can either add or subtract these equations in such a way that makes one of the variables disappear. We actually could have used this on the last example of the previous video, but we stuck with substitution on that one. So in this case, we can see that we have a match of the coefficients in front of the y's. The x's are not the same, but the y's are the same. And so what we can do in this circumstance is we can subtract these two equations. Again, we need to make sure that we have everything lined up so that our like terms are all set for subtracting each other. But if that's the case and we have a match in the coefficient in front of the same variable in both equations, we can go ahead and subtract. So 3x minus 2x is just x. 2y minus 2y is gone. That disappears, so we just get 0 out of the y's, so we can just ignore them. And then I just need to carefully subtract 8 minus 12, which hopefully we know is negative 4. And so in this case, we've already immediately gotten our value of the x-coordinate for the intersection point, but now we need to go take that and substitute it into either of the two equations to figure out what the y-coordinate is. And it doesn't matter which one, we just want to pick the equation where we think it's going to be easiest. I don't think it really makes a difference in this example, so I'll use the bottom one. So we'll go 2 times negative 4, so replace x with negative 4, plus 2y equals 12. So now I just need to solve for y. So I've got 2 times negative 4 is negative 8, plus 2y equals 12. I'm going to add 8 to both sides. So now we've got 2y equals 20. Divide by 2, and we get y equals 10. So now taken together, we have our x-coordinate, we have our y-coordinate, and so they make up the ordered pair, which is the intersection point if we had graphed these lines of negative 4, comma, 10. Now in the second example, we don't have the good fortune, like we did on the first, of having a match of the coefficient in front of one of the two variables. So the x's don't match up, we have a 3x and a 2x. The y's don't match up, we've got a 5y and a negative 3y. And so as a result, just going ahead and adding and subtracting the equations as they are now isn't going to accomplish our goal of eliminating one of the two variables, hence the name elimination. So what we're going to have to do in this circumstance is we're going to have to pick one of the two variables to eliminate. In this case, I'm going to focus in on the y's. I usually prefer to pick the ones that have opposite positive negative signs, because then if I stay with them being opposite, I'll be able to add the equations instead of having to subtract and risk making mistakes with subtraction rather than addition. And so what I have to do with the y's then, I have to somehow make them equal the same number. They can be different by a positive negative sign, that's fine, and that's actually desired, like I said, but we want to have them have the same number. And so we have to find a number that both 5 and 3 divide into evenly. Hopefully without too much trouble, we can figure that out. It's 15. So that means I need to multiply this top equation by 3. And so if we do that, I'm going to get 9x plus 15y equals negative 12. I just have to make sure that I multiply everything in that equation by 3, and then I'm going to have to multiply this bottom equation by 5. So 5 times 2x is 10x, and then I get 5 times negative 3y is negative 15y, and then finally 5 times 29, well 5 times 30 would be 150, so 5 times 29 is 1 less 5, so it's going to be 145. And so now I'm in a spot where I've got the same number, even though they're different by a positive or negative sign, in front of the y. And so that means on this one, I'm going to add the two equations. Because if I have opposite positive negative signs, adding them together is going to get them to cancel out. In the previous example, when we had the same positive negative sign in front of both of the y's, then subtracting was going to get rid of those y's. But this time, we're going to add. So I've got 9x plus 10x gives me 19x. The y's indeed cancel out, and that leaves me with 133 over here. So then we just need to divide both sides by 19, and if we need it, we can push buttons on our calculator to help us out, and so we get x equals 7. So that's half of the way that we need to get to our answer. Now I've got one of 1, 2, 3, 4 options as to where I could plug in that value of 7 to figure out what x is. I could use either of the two equations I ultimately added together, or I can go back to the originals. Usually going back to one of the originals is a good choice because the numbers are going to be smaller. And again, we just want to pick which one we think is going to be the easiest to deal with. I'm going to go ahead and use the top one this time. I don't think it makes much of a difference. So we're going to go 3 times 7, I'm plugging in 7 for x, plus 5y equals negative 4. So now I've got 21 plus 5y equals negative 4. I'm going to subtract 21 from both sides. So I've got 5y equals negative 4 minus 21 gives me negative 25. And then I just have to divide both sides by 5. And I've got y equals negative 5 as an answer. So taken together, I've got x equals 7. I've got y equals negative 5. Those are the coordinates of our intersection point. That's the solution to our system of equations.